we have this huge unconformity between the top of the chalk and the overlying Cainozoic sands. So Paleogene, what used to be called, what still are called Thanet sands, and Woolwich and Reading and London clay. And it's about 18 million years. So how can we start to explain this? There's Jenny. This is Allen Bay, and you're looking at a vertical face of chalk, which has been tilted, so it's pretty much vertical. And these are karstic swallow holes developed in the upper surface of the chalk on a land surface sometime after the unconformity developed. Obviously, it would originally have been horizontal, but has now been tilted, so it's vertical. These are essentially identical to the kind of swallow holes on the chalk that you can see across large areas of the chalklands of southern England. Well, one possible explanation which Brian Lavelle and I explored was the influence of things called mantle plumes on the succession. Now, mantle plumes start at the core mantle boundary as a thing called ultra-low velocity zone. Not as one student put, ULEZ, ultra-low emission zones. Sadiq Khan is not responsible for the mantle. And what happens is you get this plume of extremely hot mantle material coming up and eventually pushing its way up through the asthenosphere and creating a mantle plume. And they're very classic structures. You can see them. They have fingers of mantle, which it's called underplating. It's called a plume splatter. These things come up and then they spread out from the point source of the original plume. And this is the Iceland plume, or one reconstruction of it, and you can see how wide-ranging these fingers of mantle material underplating the this area of the northeast Atlantic are. Well, very interesting. If we plot, so we know all these igneous rocks in Northern Ireland and the west of Scotland, and St Kilda and all these things offshore, and Rockall and so on. And we also have these dike swarms coming down, and we have Lundy, we have all this evidence of igneous activity, which was probably related to the Iceland mantle plume. And the earliest stage of the Paleocene is missing over this entire area. So if you see the pink is the Paleocene, it's just not preserved even slightly over this area in the unconformity which sits on top of the chalk. And then down here we have another probable mantle plume in the Massif Central. So it's becoming geologically quite a complicated situation. I just love this, the way they've now mapped the extension of many of these dikes into the Dutch sector of the North Sea using seismic. So that Mull dike swarm was really a very, very major event, with dikes spreading into the South Permian Basin and into the mid-North Sea High. Anyway, John Cope noticed something very interesting, because you know that classic map of the geology of England, where you have Jurassic coming round, swinging round, and then going down to the Dorset coast. Yep. And then we have Cretaceous swinging round more or less parallel with it. Well, what he argued was that actually this is one of those fingers coming down of the mantle plume, and the formation, the outcrop of these formations was controlled by uplift, yeah? Generated as a consequence of the effects of the mantle plume. So I thought, well, let's check this out by looking at the chalk. So I spent a horribly long time looking at the age of the chalk immediately underlying the Paleogene. And it's really fascinating. So these are the youngest bits, the Maastrichtian. Remember the Maastricht Treaty? That was signed in Maastricht, but these are the youngest Cretaceous, is here in northeast Norfolk going into the North Sea, and here in the mid-channel, and then the oldest are in this area of the Chilterns here, probably extending up into Yorkshire. So it looks like the formation of the deformation of the chalk fits this story as well. But you have to remember these dips are really, really tiny. We're not talking great thicknesses, and we're not talking great dips. We're talking a fraction of a degree, but the pattern is still there, so it doesn't make any difference. And then years and years ago, one of the things that geologists loved doing was collecting fossils. Some of them still do. But these crinoids are absolutely amazing because they're worldwide. You can go to Australia. I've been to Australia and collected the same species in Western Australia. I've been to Madagascar, I've been to Texas, and I've been to Canada, and we have the same species in the same order. They're fantastic markers. And these were discovered in Surrey by a Geologists Association field trip on bicycles in 1904. And someone apparently had a puncture, and they stopped to repair the puncture and noticed fossils in the piece of chalk on the side of the ditch. And bizarrely, I ended up using that information because I wanted to reconstruct what was happening. So the brown is essentially the Paleogene, and the green is the chalk. And by plotting all these distributions of the fossils they found, you can show that there's Dorking, just to show I know where I am, and there's Guildford, and underneath this area is a syncline. It's a very gentle westerly plunging syncline, which we can delimit from these chalk fossils. So this is how I built that map of the chalk underneath the Paleogene up. It was a real pain in the arse. And then, Brian, why don't we do the Paris Basin, Brian said. So I did the Paris Basin as well, using the BRGM Digimap, and then an old French atlas, and going through and marking the age of every spot. And we end up with quite interesting structural pattern, really. We have this syncline in the channel, we have the North Sea Basin here with the youngest strata preserved, and then down here we have this enormous uplift associated with the Massif Central, which, anyway, we argued that some of this was controlled both by the Mantle, Plume, and so we put all this together, and it's really very, very interesting if we do. So this is the time scale up here. This is what's happening in the North Sea, and this is the gap. So with nothing in it is the gap, and there seems to be a major uplift about 61 to 62 million years ago, and all of that chalk was uplifted and eroded, and there was a change in the sedimentation from the carbonate. So the chalk, people don't realize this, the chalk extended way, way, way beyond the Cretaceous in the North Sea and across large areas of Europe and Asia. And the big change to clastic sediments occurred 4 or 5 million years later. And that seems to be exactly coincident with the big uplift. And then immediately after that uplift, we have those North Atlantic igneous province intrusions and extrusions. So the Antrim basalts kick off exactly here, Ailsa Craig and all of those igneous rocks in the north. So it looks as if this was the big uplift was the immediate predecessor to the eruption and intrusion of those igneous rocks. And then if you go to the North Sea, Denmark, Netherlands, central southern North Sea, France, Belgium, you have massive floods of chalk, reworked chalk, coming off into the stratigraphy, coming off the uplifted chalky areas. So what can we do with this? Well, I discovered something very interesting by plotting the accumulation rates or depositional rates of chalk, that they end up being pretty much the same once you've gotten above a certain level. So I was able to work out, at least in theory, how much chalk had been stripped off. And I won't go into this in detail, but in the maximum seems to be in the Chilterns, where approximately 500 meters of chalk had been removed. After that uplift, it was simply penoplaned off, and that chalk was mostly washed into the North Sea basin, where it contributes to the sediment there.